It's our great pleasure to have a Professor Richard Teeuw uh, of the University of Portsmouth, UK, to present the presentation entitled Uses of Earth Observation, Big Data, and Analytic for Coastal Risk Management. Um, so yeah, so the time's yours. Okay, we can
Well,
start.
thank you. Thank you very much. Hello, everyone. It's a pleasure for me to give this presentation to the Taiwan Space Union. I'll be talking about uses of Earth observation, big data analytics in coastal risk management, and I'll be illustrating that with examples from the South Pacific, the Caribbean, and also the Mediterranean. I thought, first of all, it would be good just to review the many uses of Earth observation data for disaster management, and we can best do that via the disaster management cycle. You can see that there are various stages that we go through before disasters. Then much of the work that I've been doing over the past few years has been on mapping of hazardous terrain, and more recently vulnerable features, and also reconstruction materials potentially for post-disaster reconstruction. That's all done at a steady pace, but things really change then as we move towards preparedness with early warning systems. That's also particularly important from the point of view of giving alerts and also working on public education to raise awareness of what to do in different types of disaster situations. A very different stage then requiring very rapid processing of data, and ideally daily or imagery that's available many times a day, is in the response phase for the guiding the search and rescue, where often we only have 48 hours or so to find most of the survivors alive. Therefore, there's a big imperative to act quickly. But there's also then the selection of areas that are safe for shelters for displaced people's camps and the like. And then we're into a stage after the disaster for monitoring the reconstruction and rebuilding of infrastructure. I'm working primarily on the mitigation and preparation side of things, and that's where these examples will come from. Now, big data analytics is something that we've always had with satellite imagery. They tend to be quite big files that upset my computer staff at the University of Portsmouth. We're dealing now, though, with huge amounts of data. Those satellites that we have are moving from weekly revisits to daily, or sometimes many times daily, thanks to constellations of microsatellites. And very importantly as well, we're moving from pixel sizes ranging from 30 megapixels down to 10 centimeter pixels. And we also have uncrewed aerial systems or drones, which can give us the information, the data down at centimeter to millimeter detail. So there's a very urgent need for faster, better computational methods to process those Earth observation data pools, because they're fast becoming data oceans. Three main uses that we're going to be using in terms of improving our processing of the data, our use of the data. That's feature identification, whether it's spatial or spectral, for instance, for roads, buildings, crop types. Then there's change analysis, such as deforestation or storm damage to crops, for instance. And then there's time series analysis over years or decades, where we're seeking temporal patterns. The case studies that I've got for you are from islands and from coastal disaster risk management projects. The first one is from South Pacific archipelago states, and that's primarily where we're using satellite-derived bathymetry along with satellite elevation models. I've included as well an example from Crete, which is a mountainous island in the Mediterranean, very prone to disaster, well, prone to occasional very severe disasters from earthquakes. And that's more terrain analysis and seismic risk mapping. The first example uses some machine learning, and we use Google Earth Engine a lot for that. The Crete example is where we use a lot of multi-criteria decision analysis. The final example is from the Caribbean, from Dominica, and this is really getting into a lot more detail. It's looking at the development of a very basic digital twin, which then supports a decision support system for storm resilience in communities. And that data is primarily derived from drone imagery and photogrammetry, and from some LiDAR aerial imagery, and from mobile phone app at house-to-house levels of detail. So we're going from archipelago states, which cover millions of square kilometers, right the way down to individual households. The first project is the Common Sensing Project. This was a very large project running over 4 years, involving a lot of big organizations. It was led by the United Institute of Training and Research, along with the UK Satellite Applications Catapult. It involved the UK Commonwealth, Sensonomic as well, DevEx, and the UK Meteorological Office, as well as the University of Portsmouth. And the idea was basically for the island states of Fiji, Vanuatu, and the Solomon Islands, which we can see here in the South Pacific, was to help build climate change resilience in those small island developing states. They're not just small island developing states, they're also archipelago states spread over very large areas. And all in all, there's over 1,400 islands in those countries. The aims were to improve access to climate finance by producing better maps of the areas at risk, and seeking measures, therefore, to reduce those risks through disaster risk reduction programs, to enhance food security, and to build enhanced resilience to climate change. For my part, I was involved with a team that was developing 2 new data layers. One of those was for elevation and slope hazards, prone to waterlogging, prone to slope instability, prone to flooding, and it included the low elevation coastal zone, i.e. all the land which is less than 10 meters above sea level. And the main data set we used for that was freely available Alice Pulsar Global DM with 12 meter pixels, which we could get from the University of Alaska. And we also then were producing a satellite-derived bathymetry layer with the idea of showing the run-up hazard around these islands. And that was from the 10 meter pixel Sentinel-2 imagery. And it produced nearshore relative bathymetry maps down to depths of approximately 30 meters, particularly accurate to 20 meters, less so for 30 meters. But we only needed an approximation, really, to indicate the areas which were most at risk for run-up from tsunamis or from storm surges. And then there were some other analysis-ready map layers that were produced, such as cloud-free mosaics for the islands, maps of vegetation cover, flood susceptibility, and areas of urbanization. This is an example of the outputs from that project for the Solomon Islands, approximately 900 islands. And it shows you that all of the islands were covered. It wasn't just the major capital island, Guadalcanal, and the capital, Honiara City. For many small island developing states, you only find it's the main island, the capital island, that gets most of the mapping. Therefore, all the outlying islands tend to have very minimal mapping. By using satellite data, DEMs, and then the satellite-derived bathymetry, we were able to get archipelago-wide mapping, both DMs and also for the satellite-derived bathymetry for Vanuatu, for Fiji, and that included those low-elevation coastal zones, which were partly important from the point of view of coastal hazards, but were also important for assessing areas of mangrove, either existing or potentially former mangrove, from the point of view of blue carbon, because various grants are available from regional development banks for protecting those areas and for carbon sequestration through mangrove and occasionally seagrass. And we're going to go through a sequence now of looking at the main island of the Solomon Islands, Honiara, and the capital area, Honiara City, and the nearby airport. This just shows you what's available in terms of accessing the data. It's open to the public. That will be via the National Disaster Management Offices in Fiji, Vanuatu, and the Solomon Islands. And that's what this screenshot is of the main island, Guadalcanal. And then the red circle, red square is over the capital, Honiara. The data is also hosted by UNITAR and the UK Satellite Applications Catapult. And you can see there that a user can go in and in this case access the elevation zones, but they can also access the relative bathymetry. And if they go in, they've then got data that can be processed. This processing is done using QGIS and with overlays from OpenStreetMap. But it gives you that key baseline data that you can work on from the point of view here of this set where we've got the elevation for Honiara City and the airport. The city's in the center. The airport is the rectangular feature over to the right. We can also see actually quite an early attempt at mapping the relative bathymetry. That was refined somewhat since then. There are issues there with turbidity in the water that was literally clouding that to some degree, but we can pick out the areas where we do have something a shore bench which is likely to give a run-up effect, and interestingly that is very close to the airport, which is a major area of development with commercial districts and a lot of new housing as well. And on the lower level we've then got detail around the city centre and the port from the Alos Pulsar elevation model processed to give us slope steepness, and there's a lot of cliffs in there in quite densely populated areas. And we've an overlay there from OpenStreetMap. And we can also use that data set then for modeling what if we get 10 meters of inundation. Quite important here because Honiara is prone to tsunamis. They've certainly hit other parts of the Solomon Islands. And at the time we made this map, the office of the Solomon Islands National Disaster Management Office was right on the coast, right next to the sea. And within probably 2 or 3 meters of sea level. There are already plans to move that up above these cliffs that you can begin to see highlighted quite close into the city, but another 40 or 50 meters up above sea level. This then shows you two things actually. On the left, we've got all of the islands, all the archipelago states, and you can see a combination of the satellite-derived bathymetry with the low elevation coastal zone. So you get an idea of the wide area that was coverage and mapping that was done in a relatively short time, a few months effectively, as opposed to the many years it would take if you were to go out and do traditional surveys of all of these different islands. So that's where satellite Earth observation is a definite plus, a huge saving. And then we can see what happens when you take the data that we've got there for the low elevation coastal zone and for relative bathymetry down to approximately 30 meters. And then we work with GIS to overlay OpenStreetMap for the drainage network and the transport network. We can straight away see those areas where you're likely to get coastal run-up, and therefore communities along those coastal zones facing that run-up effect can be forewarned, and you can therefore put evacuation routes in place up to higher ground or to large multi-story buildings that are made of reinforced concrete as shelters. But you can also see with the transport network, we can mark those points where we've got roads crossing over streams where bridges, there's a possibility, say in a cyclone, that you're going to get those bridges washed out or landslides affecting the roads. It gives you an idea of how much more vulnerable some districts are relative to others in terms of access after a major cyclone event, for instance. And you can zoom into great detail here if necessary. I'm just giving you the overview of the main island of Fiji with this particular example. The next example I've got is from the island of Crete on the southern side of Greece. And it's located really at a point at which Africa is colliding with Europe. So it gets regular, very small earthquakes in the order of 1 or 2, magnitude 1 or 2. But every few hundred years to 1,000 years, about 1,000 years ago was the last really big earthquake, magnitude 8. And then in that earthquake, you had major displacements in the order of 5 to 10 meters in places. So it's seismically active, but with occasional devastating earthquakes. And what we've done with this was from a PhD student at the time, Teeuw, who's since worked me on many more projects, including that project out in the South Pacific. But what was done here was taking the elevation models for Crete and then looking at the drainage basins and the drainage systems in particular, and looking for deformation in the drainage, which has taken place over hundreds or thousands of years. So you're picking up the gradual neotectonic deformation of landscapes. And for that, we use multi-criteria decision analysis with based around analytical hierarchy process and a weighted linear combination for half a dozen different types of geomorphometric maps derived from SRTM global digital elevation model. But we also went further and thought, well, okay, we can map where the neotenic deformation hazard is, highlighting those places where the tectonic stress is building up. We also wanted to add to that information about the population and infrastructure, the road network and public buildings, built up areas. And from that, through the multi-criteria decision analysis, we could pull both the socioeconomic information in alongside the physical geological information and come up with a seismic risk map. Just to illustrate the different layers that went in there: slope gradient, amplitude relief, river gradients, and then the lithologies, how consolidated they were, along with lineament density. They are all examples of the layers that were fed into that, the data layers. And if we then get our neotectonic deformation map, that's on the left-hand side. That's simply derived from a digital elevation model and geomorphometrics. We can take data from seismic observatories on the ongoing seismic activity and where that occurs and where it's most frequent. We can look at the population and the distribution of critical infrastructure, and we can come up with a seismic risk map. Now, on the top right, I just put on for comparison a map of Crete that's been derived from Sentinel-1 satellite interferometry, primarily Sentinel-1. So there we're getting deformation based on millimeters per year of deformation. But there is a lot of similarities then between what we get from the approach, which is based on thousands of years of landscape deformation with geomorphometric analysis and then the multi-criteria decision analysis. There's quite a similarity between that. Both can be used together. I wouldn't say anyone is more effective than the other. But if you're in a country where there isn't a particularly good coverage, say, for INSAR, then you've also got this approach based on digital elevation models and geomorphometrics and the various geomorphometric parameters that can be used and combined then to give you neotectonic deformation hazard. I thought that might be interesting in the context of Taiwan being a mountainous country that's particularly prone to tectonic hazards. The final example I want to give you is from the Caribbean, and that is on geoinformatics and digital twins for hurricane risk management, aiming at improved community resilience. And this is a project that's being carried out again with Teeuw, but also with colleagues in Italy at the Cassandra Architectural Consultancy. We've done quite a bit of work in the Caribbean over many years, particularly around Dominica. And so we were pretty fast on the scene after Hurricane Maria, Category 5, the most severe type of hurricane, hit Dominica. A dead-on hit, went straight over the island in September 2017. We were out there a few months after the initial search and recovery phase, once things had calmed down a bit at the start of 2018. And we looked at a number of villages, and we were particularly interested in which areas were most affected by the hurricane and then the coastal storm surge as well as landslides and debris flows in the interior of the country. You can see a map here of Dominica on the right, showing the elevation. You've got a line of 9 major volcanic areas, which are semi-active. They've got hot springs and things like that. They're not actually erupting, they're kind of bubbling away. And then you've got the road network and drainage network overlaying on that from OpenStreetMap. And you can see the circled area here on the Caribbean coast. This is the village of Coulibaly, which is one of the focuses of the study. We looked at 2 or 3 other areas, but this is the one that I'll show you. We focused on this valley. It's got issues with landslides, debris flows coming down the river system, as well as the coastal zone severely affected by storm surges. We were funded by the UK Natural Environment Research Council. The idea was to assess what went wrong, what went wrong, also what worked, what survived, particularly with the likes of bridges. It was devastating mainly because of the debris flows that came down the steep mountain slopes when they had the large amounts of rainfall from the hurricane. And those produced boulders sometimes as large as cars, which even if you had reinforced concrete buildings but were too close to a drainage channel, your building was likely to be severely damaged, if not destroyed. A lot of undercutting of bridges, various types of failure there. We also, in terms of, as well as the building and infrastructure data, we did surveys of the terrain. We were lucky to have a laser scanning LiDAR elevation model for the island, flown by aircraft, but we also had drones. We flew 40 sites that were severely impacted, damage to infrastructure and houses and fatalities. Those are all surveyed and then mapped and assessed. We also then carried out computational fluid dynamics on a number of areas. The example here is for the village of Coulibaly. I'll come to that later. And then we did building surveys, something we developed actually on the Common Sensing project in the South Pacific. And we went round all the buildings then, or a sample of 100 buildings in that village, and we got the conditions, the building conditions. There was social environmental data to do with the different settings of the buildings, whether they were valley floor, coastal, hillside, and so on, as well as quality of life surveys and socioeconomic vulnerability surveys. All of that information was then fed into a decision support system, which was developed in conjunction with the Cassandra consultancy. And this is some examples then of the decision support system. In this case, for the buildings category, that was the focus of this. It does cover other features as well. And we had the data coming from the mobile phone app, photographs, and then a checklist in the app as to the construction type and number of stories of the building and so on. We also then flew the area with a drone, so we can see here the drone imagery overlaying on top of the a 3D point cloud model of the area, giving some color to the different buildings. But from that, we went on to develop a overlay on top of the landscape, and we separated that further into a virtual twin, digital twin, for each building and each tree that was in that particular community. For the valley itself then, because we had the whole landscape there from the LiDAR imagery, we were then able to run the fluid dynamic modeling where we can see wind velocity and pressure color coded here. So red is the higher velocity and pressure that we've got, blue are the relatively quieter areas, and we got some funneling effect coming down the valley, as you might expect. And also we could get down to the scale of individual houses, and we could consider the house shape, such as the roof pitch, things such as the proximity of the house to the river running through the village. And we could also do what if scenarios. What if there were tree breaks in front of a particular house? That's quite interesting, because having the trees there can be a very useful thing. We can see that the view of the house without the trees, you've got pressure points developing around the top of the roof. Once those trees are in place, then they're breaking up the flow of air, and we've got much lower velocities and much lower pressures over the house. It's interesting also from the point of view of climate change. Heat waves are getting to be more and more of a problem in the Caribbean. So having the trees there as well could also be a big plus from the point of view of reducing the impact of the heat stress hazard. That information is then fed through from the data that was collected in terms of the geographical data, in terms of the morphology of the land, distance from the river, for instance. Also the physical data in terms of the building type, the height of the eaves of the roof, whether there were porches, the construction type, the shape of the building, whether it was rectangular or round, and so on. And then we had a land use category as well that was fed into the decision support system, just for this one category of housing. And from that, you get a resilience score. So the current condition, the resilience score was at 58% based on the parameters that we've looked at. So it's an arbitrary score, but you can then start to say, well, what if we change this feature? What if we change that feature? In terms of either the building shape or the locations of buildings relative to the stream and relative to the coast, for instance. And in this example, the what if scenario was, what if we move buildings that were within 50 meters of the river? What if we clear those? How does that improve the resilient index? Well, it does improve it, only goes up a little bit, 59%, but there's a definite increase in that resilience index from that particular scenario. So there are dozens of different scenarios that were tried. I'm just giving you one example here. So this, I think, is showing how we've gone from looking at whole island states, archipelago states, and then been able to move into detail for individual communities in terms of the hazards that they face from slopes or from their coastal geomorphology and potential run-up effect from waves, making use of the bathymetry data along that coast. But we can also then move into more detail then potentially by getting more detailed surveys using the mobile phone app, by using drone data to collect data sets that allow us to do photogrammetric 3D models from which we can then derive basic digital twins, which we can then use for our modeling of, in this case, primarily climate change issues, what was likely to be happening over the next 10 to 20 years or so, and how to better prepare for that. So whether that Cassandra decision support system will improve community resilience, that's a moot question. I think it's particularly useful because it's able to move from landscape scale down to village scale and consider the geometry of the village, the layout of the village, as well as also the building design itself. We were able to integrate in that one different types of data. We work primarily with aerial LiDAR surveys and then with drone photography. We integrated that with mobile phone app data and with social survey data. If we didn't have the LiDAR data, we could have done what we did out in the South Pacific and used the Alice Pulsar 12-meter DEM, global DEM. And we'd still get some particularly useful results in terms of guiding the community and the local government in the best ways of perhaps redesigning some aspects of the village to make it more resilient to impacts of extreme weather events in this case. And then the architects were able to develop optimal scenarios to adapt existing buildings and design more resilient buildings. And you see the architect sketch there on the right of what they saw then as the optimal building to cope with the Caribbean weather conditions of the windstorms, but also the issues with increasingly warmer temperatures. Further research is looking at that aspect, the temperature data analysis, and then also seeing how we can make the decision support system a bit more sophisticated by incorporating multi-criteria decision analysis. So really, this is a closing slide, actually. It's the idea of when doing this, it might be coastal risk management work, disaster risk management work, but it's wise to have a catchment to coast approach rather than simply focusing on the coastal area. It's important to understand what's happening with the drainage basins in the interior. There's a lot of information you can get from that, whether it's to do with deforestation, perhaps illegal mining or pollution. Potentially from the drainage basins, you can also begin to derive some neotectonic deformation information. It's also important to have the mobile phone link, have an app that can be used. We used EpiCollect, which is a freely available mobile phone app, developed initially for epidemiology, but it was readily modified for carrying out building inventories or inventories of bridges, which can then, as you can see on that map on the right for Fiji, it can then be put into a database, spatial database, which will show you the locations of those photographs and the little database that is collected for each feature. It's a two-way thing with that mobile phone, though, because it can also be used potentially, if you've got an app, you could have the public crowd sensing, collecting data for you, but you could also use the same app to send out messages to the people using the app, perhaps asking them to look at the database of the local disaster management organization to double check on warnings for particular hazard events. So it could become a tool that could be used not just to collect data, but could be used for hazard assessments. It could also be used as a tool for informing the public. But all of that is feeding then into APIs. We've got some big data analytics going in there with machine learning and AI. We've got the data coming in from our satellites, Landsat, Sentinel-2 for a lot of the land cover data, but also for monitoring turbidity traveling down rivers to the sea, having an impact on the coastal zone, both on deposition and erosion, but also potentially on pollution. And we've got those elevation models as well, which are going to be for the drainage basins, the river network, geohazard zones as well. And all of that is then feeding into, ideally, a satellite-guided coastal risk management system. So the focus perhaps is on the coast, but you really need to include also the drainage basins that are linked in and transporting material and other primarily various types of material down to the coast. I've given some publications here. These all are ones that are relevant to what I've been talking about here. So hopefully you can go back and look at things in more detail. But that concludes my talk. Thank you very much. Are there any questions?
Thank you so much. It's a very excellent talk and learned a lot from it. Yeah, we open for questions. If you have any question, please raise your hand. And maybe I can ask the first question. So I'm wondering that when you show very nice plans and the risk, I'm wondering that using the remote sensing and satellite data, various data set, I'm wondering that do you have a different time scale of a latency time? For example, if you have the risk for like next week, next month, or 6 months later, or something like that. Do you do that kind of a different time scale of the risk and warning? I'm just curious. And in that sense, what kind of a future satellite data would be needed if you want to, for example, improving the latency? Yeah. So it's kind of like a twofold of a question. Yeah. Thank you.
Yeah. Yep. My notepad. Yeah, I wouldn't say that we're building in a latency aspect to it. I mean, there's the latency of getting the data and processing the data, but that aspect of latency is greatly reduced with new satellites because most of them have got AI built into the sensors anyway to only pick out those features that are particularly useful. The easiest one would be to only detect water if we're looking at areas of flood hazard or flood events. Therefore, there's less data to stream down to the ground and there's less pre-processing going on to produce the maps of the areas that have been inundated by water in that flood event. So that speeded things up by doing on the satellite data processing to reduce the amount of data that has to be streamed to the ground and to reduce the data processing time. So that's a plus with latency there. The other aspect as well that links to it is the fact that we now have many constellations of satellites which are increasing in the numbers of different types, but also the numbers of microsatellites involved with each constellation. PlanetScope, for instance, now has enough satellites in its PlanetScope constellation to give you 2 or 3 times a day, at least, just about anywhere in the world of coverage. You still have the problem with clouds, but you're possibly going to find gaps in those clouds for the feature that you're trying to identify. It's proved particularly useful, for instance, with tracking damage from cyclones in the South Pacific, where we could, within 1 day, show just from PlanetScope, show the bridges and roads that were closed, destroyed as a result of Cyclone Harold, I think in 2020, over Vanuatu and also parts of Fiji. That was done within a day of that cyclone passing by and was fed straight over to the UN, who were then able to guide the Vanuatu authorities in the allocation of response teams. Latency from the point of view, it depends on the hazard. A lot of those are flood hazards and landslides associated with them. When it comes to earthquakes, well, not really, because you're into the issue of your seismic gaps and trying to plan for when the next likely earthquake's going to be. You probably appreciate very well with your own issues with earthquakes that predicting the most likely area that they'll affect is very difficult, and saying it's likely to occur in the next year or so. People have tried that. It never really has happened. There is, however, what you can to some degree look at trends in urbanization and certainly begin to predict which areas you've got a trend towards deforestation and urbanization, which is almost certainly going to increase the flood risk in a given valley over time. You can begin to predict that and at least warn government authorities that they need to improve their regulations on planning, perhaps, to stop that happening. But you can quite easily look at trends over 10, 20 years and begin to see where the trends are for urbanization in that sense. So you can sort of predict where the risk is going up, because the increase in vulnerable features, infrastructure and people is likely to increase over time. So I hope that's answered your question or your questions.
Yeah. Yes, it's very helpful. Thank you so much. I wonder if Professor 吴朱恩老师有在线上吗？我看到吴老师有在。吴老师有问题吗？Really expert.
Yes. Okay. Thanks, Professor Teeuw. Okay. Thank you for sharing so many experience and the technology of coastal risk management system. I've been to Solomon Island, and I'm doing the tsunami and the storm surge research. So when I was there, they asked me one interesting question. They say their capital, okay, very close to the coastline, okay, and the entire Solomon Islands are just nearby a large change. That means they are under a big threat from the larger earthquake. And then they also understand that after the large earthquake, they might have tsunami. Okay, so then they asked me, what if they know there's an earthquake? And then, the earthquake, they should go to the lower ground. And later on, they will have tsunami. Then they have to climb up to a higher ground. So for this kind of multi-hazard scenario, do you have any suggestion or comment on how to make make them safe, or let's say the resilience, make the resilience better?
Mm-hmm. Yeah, sure. That there should be available from the government in the Solomon Islands and for also the governments in Fiji and Vanuatu, the very basic digital elevation maps that we produced from the Alice Pulsar 12-meter pixel data set. We did that in different zones. We did the low elevation coastal zone of everything below 10 meters above sea level, which you could look at as being particularly high risk in the event of a tsunami event. But we then also then had the next slope category we did was 10 meters to 40 meters, because we found most of the habitations were in that zone. And also, if you want to be particularly safe from a tsunami event, let's assume it's something that's over 20 meters high, then you probably want to be looking to be at the top of that zone, approximately, say, 40 meters, 30 to 40 meters, and having some pre-prepared cleared areas as shelters, if you want, for displaced people to go to. I've seen that work particularly well in Sri Lanka. I was there a few years after the 2004 Indian Ocean tsunami. So the people there were knew that they had to respond to early warnings and evacuation sirens. And while I was there, the sirens went off, and I stayed with the people I was staying with. We all just walked very calmly. The whole village just moved up to a nearby hillside where there was a pre-prepared trackway and a cleared area that a few hundred people could gather. I was very impressed with how calm people were, because the thought of a repeat of 2004 was obviously something that could terrify people. But these pre-prepared areas were there, and there were regular drills as well to practice on using them. So I think having the digital elevation model data is really useful for getting those preparedness maps. Also important was the awareness raising of the general public, and that worked very well. A lot of what we did on the Common Sensing project was also training courses for capacity building, primarily through universities. We would try and work through the universities so that they could incorporate through maybe the geography department or maybe a civil engineering department the use of the GIS, but primarily QGIS again, because it's free open source software, so there's no cost barrier. All of the data provided by the Common Sensing project was freely available as well. So we were reducing cost barriers, training up people to use them, and hoping to raise awareness. But the maps should guide you in the areas which are most at risk, and then the locations of potential safe refuge areas for people to go to.
I see. Very good comment. That means I'll prepare that kind of a map for higher ground and education, and also the training for how to escape. Okay, that's very important. Well, agreed, and very useful. Thank you very much.
You're welcome. You're welcome. For the sustainability side, I think it is very important to try and work with local universities and try and get students aware of this, because they're the ones who are going to go out and maybe become future government officials or work with businesses who can be decision makers. And also there's a degree of sustainability because the information on disaster education and how to use the various satellite data sets or make use of pre-prepared analysis ready data sets could stay within the curriculum. It's referred to on a regular basis rather than forgotten about in a cupboard or a hard disk in some cupboard locked away in a distant room somewhere in a government building.
Mm-hmm. Good point. Thank you.
Okay, thank you. So, are there any further questions from the audience? 谢谢吴老师哦，谢谢。
太客气了，不会不会。
Yeah, I think we are very impressed by how much effort you have been working on that, and there are much more details you have presented than we imagined before coming to your presentation. Yeah. So any further questions from the audience? If not, so let's give a big hand to Professor Teeuw again for this very exciting presentation. Thank you so much for presenting this to us. This is very useful to us. Oh, 刚有人有问题吗? No? Okay, I saw somebody raise their hand. Okay, so thank you again, Professor Teeuw. So yeah, looking forward to interact with you further in the near future.
Thank you. It was a pleasure and a really interesting discussion as well. Thank you very much.
Thank you.
Thank you so much.
那任凯我们就在这边结束会议吗？是不是？
好，谢谢。
好，谢谢老师。
Okay, so yeah, so we will close our seminar today. Thank you all for coming. Thank you.
Goodbye.
Bye bye.
Goodbye, sir.